Hi, I'm Carl. I'm an engineer here at the factory. I'm here to help you train on non-permanent joints in the context of manufacturing assembly methods. In this module, we'll discuss non-permanent joints. Our goals will be to list different types of non-permanent joints, to select a variety of fastener types for typical joint applications, to identify the attributes of common fasteners, to select appropriate tools and assembly techniques for joint applications, and to understand design considerations for joint and fastener selection. A mechanical joint is a section of a machine which is used to connect one or more mechanical parts. Joints may be classified as non-permanent or permanent. Most industrial machine joint types are non-permanent. That is, they're designed to be disassembled or easily separated. They're temporary. Now, some mechanical joints are designed to allow relative movement of mechanical parts in one degree of freedom and restrict movement in another. While permanent joints, such as welded frames, glued joints, or riveted aircraft structures, are not easily separated. In this module, we'll mainly discuss non-permanent mechanical joints. Permanent joints will be discussed in another module. Some of the reasons for non-permanent joining and fastening include field assembly, replacement of parts, disassembly or ease of disassembly, maintenance, repair, and adjustment. Here we see an example of a typical industrial machine with a number of parts assembled and joined together. The machine has several structural members, motors, and a linear rail system. It is obviously designed for some type of moving process, perhaps controlling a raw material or a tool along a flat surface. We'll call the vertical plate with the black dots on the side a carriage, and the upper structural member it's attached to, extending horizontally, a bar. The fasteners joining the carriage and the bar are typical socket cap screws. A socket cap screw, also known as a socket head, cap screw, socket screw, or Allen bolt, is a type of screw with a cylindrical head and a hexagonal drive hole. A socket cap screw typically has a head diameter that's nominally about 1.5 times that of the screw shank diameter, with a head height about equal to the shank diameter. These are typically high-strength fasteners intended for demanding mechanical applications, sometimes made with special alloys capable of maintaining strength at high temperatures. A hex key, or Allen wrench or hex driver, is required to tighten or loosen a socket screw. We can think of a non-permanent joint as having a base and a secondary part. The base frame, or part of the joint assembly, is the horizontal bar in this case. It includes a blind threaded hole or holes with a flat mating surface. The holes must be drilled and tapped to allow the cap screws to be tightened into the base part. The secondary part, the vertical carriage in this case, is mated to the base and joined with several screws. There's a pattern of through holes aligned for the socket cap screws. We can see how use of non-permanent joinery allows for ease of assembly and disassembly, possibly replacement, maintenance, repair, or just adjustment. Note that the socket head cap screws are commonly used in assemblies such as this that don't provide sufficient clearance for a conventional wrench or socket. There are a wide variety of non-permanent joint types, with bolted and screwed joint assemblies being the most common. Pictured here, we see a hydraulic pump with its numerous internal moving parts sandwiched together by two outer plates and 4 screws. On the bottom left, we see a typical structural lap joint with 5 bolts and nuts and 2 overlapping structural members. In the middle, we see 2 80-20 structural channels held together with an angle bracket and screws that tighten sliding nuts inside the slots. Engineers often use 80-20 for frames and prototypes because of its adjustability. On the bottom right, there is a flanged pipe assembly joined by a high-density pattern of bolts around the flange circumference. Bolted and screwed joints are easy to design, assemble, and disassemble for service and repair, and they allow procurement of standard low-cost fasteners. But they have disadvantages which include possible loosening of joints and fatigue failure of threaded components. There are some other common joint types. Revolute pin joints allow rotation along an axis. Prismatic joints allow sliding movement. And ball and socket joints allow spherical rotation. There are many other joint types, and it's helpful to take a look at wood joinery for some examples. A butt joint is the simplest but weakest joint. For a butt joint, the flat end of a piece of material is butted or mated against another part with a flat face. When the end of a part is laid over and connected to another part of an assembly, it's called a lap joint. Lap joint types include half lap, cross lap, mitered half lap, and dovetail cross lap. The added surface area increases joint strength, and lap geometry aids alignment. This holds true for industrial machine assembly just as much as woodworking. Some other wood joints include a mitered joint. It's similar to a butt joint, but both pieces have been beveled, usually at 45 degrees. A dovetail joint is a form of a box joint where the fingers are locked together by diagonal cuts. A bridle joint, often known as an open tenon or open mortise and tenon, or even tongue and fork joint, is where the through mortise is open in one side and forms a fork shape. The mate has a through tenon or neck joint. A mortise and tenon, the stub, the tenon, will fit tightly into a hole cut for it, that's the mortise. A dowel joint, which is a butt joint reinforced with dowel pins, or a crossed dowel joint, which has a threaded metal dowel that's inserted into a drilled slot. A screw is then inserted through an opposing slot and tightened to create a pull effect. There's also dado and groove and tongue and groove, cross lap, splice, and beveled scarf joint, just to name a few. Again, strength and alignment are key factors in joint design. Generally, increasing surface area is the surest way to increase strength, and adding fasteners such as bolts or dowel pins or screws often strengthens the joint and allows for alignment, assembly, and disassembly. Many other mechanical joints are sealed or gasketed. A seal is a device or a material that helps join systems, mechanisms, or other materials together, preventing leakage, for example in a pumping system, containing pressure, or excluding contamination. The effectiveness of a seal is dependent on adhesion in the case of sealants and compression in the case of gaskets. The seals are installed in pumps in a wide range of industries, including chemicals, water supply, paper production, food processing, and many other applications. There are many design considerations for joint assembly. Many depend on the application. A lawnmower blade assembly demonstrates an example of a simple mechanical joint with several design concerns. The rotating blade results in dynamic combined loading with vibration expected. Loadings to consider might include torsion, tension, compression, shear, bending, pressure, and other forms of combined loading. Bolts and screws must have the proper strength or grade. They must be torqued appropriately to ensure clamping force and have adequate thread engagement. With spinning machinery, we might consider left-handed or right-handed threads, depending on the direction of rotation of the component, and we want to ensure that it doesn't loosen. We might also use Belleville washers to apply a flexible preload or distribute clamping force. We might also use washers for spacing. And we might consider disassembly and assembly for blade replacement and service. We know that the blade is a wear part. And we might consider alignment pins to ensure accurate and repeatable assembly. Here we see a variety of fasteners. A fastener is a hardware device that mechanically joins two or more objects or parts together. Screws, bolts, and nuts, like those pictured here, are some of the most common examples, but there are many other types of fastening hardware. Fasteners, of course, are generally used to create non-permanent joints that can be removed, disassembled, or dismantled without damaging the joining components. Threaded fastener is the name for a fastener that has a screw thread on some portion of its body. The fastener page of the McMaster-Carr Industrial Catalog shows the huge variety of joint hardware. Most non-permanent joints use standard screws and bolts as fasteners. But consider the many types of bolts one can use. Hex bolts, socket cap screws, carriage bolts, eye bolts, all thread, toggle bolts, lag bolts, sex bolts, and U-bolts, each fastener designed for a specific application. Beyond screws and bolts, there are many more types of fasteners to employ, including hook and loop or Velcro, snaps, pins, clevises, retaining rings, cable ties, snaps, buttons, hose clamps, shackles, clasps, grommets, turnbuckles. The list of possible fasteners is almost endless. Here we see a variety of hardware used for non-permanent joining. A screw is the term used for a threaded fastener with or without a head so designed as to permit it to be properly assembled in a preformed internal threaded hole, or forming its own thread and secured by means of tightening the head. The screw thread, often shortened to thread, is a helical structure used to convert between rotational and linear movement or force. A screw thread is an inclined plane wrapped around a cylinder for a straight thread or a cone for a tapered thread. A set screw is a headless threaded fastener that is typically used to hold a sleeve, collar, or gear on a shaft to prevent relative motion. A bolt is the term used for a threaded fastener with a head designed to be used in conjunction with and properly assembled by means of tightening a nut. It's common to use the terms screw and bolt interchangeably. A nut is a geometrically designed block, usually of metal or plastic, with an internal thread and designed to be assembled in conjunction with a bolt or a screw. A lock nut has a special design that helps to prevent the nut from loosening. Prevailing torque nut is a type of lock nut to assist in preventing self-loosening. There are two main types of prevailing torque nuts, all metal and nylon insert. The all-metal torque prevailing nuts generally gain a prevailing torque by distorting the threads at the top of the nut by some means, while nylon insert torque prevailing nuts utilize a nylon or some other polymer insert to achieve a prevailing torque. A washer is a part having a centrally located hole. The washer performs various functions when assembled between bearing surfaces of a fastener and the part being attached. A washer face has a circular boss under the head of the fastener, providing a bearing surface. A split washer helps prevent loosening from small vibrations. A stud is a headless fastener which is threaded at both ends of the shank. One end is inserted into an internally tapped hole and tightened with a nut on the other side to induce tension. If a stud is threaded its entire length and the nut is used on both ends, it serves the function of a bolt and is then classified as a stud bolt. It's common to see studs used in internal combustion engines. Joining machine parts typically requires multiple joining fasteners, often combined together. Understanding standardization of screws and fasteners is critical for design and assembly of machinery. There are more standardized screws produced each year than any other machine element. Threaded fasteners are produced according to one of several standards. Standards development organizations include the American National Standards Institute, ANSI, the American Society of Mechanical Engineers, ASME, SAE International, and the International Organization for Standardization, ISO. Several standards are shown on the right. Inch thread sizes are specified by a diameter and threads per inch. Diameter is also known as the thread size. For diameter smaller than 1/4 inch, screw size is indicated by a number as shown in the table. Pictured at the top, we see examples of size 10 socket cap screws. They have a 0.190 inch diameter. These threads come in coarse 1024 and fine 1032 threads. 24 and 32 correspond to the number of threads per inch. We also see similar metric screws designated by M. The number next to M corresponds to the thread diameter in millimeters. Next to that, we see an X or a multiply symbol and another number corresponding to the millimeter distance between threads. Again, we see coarse M6 by 1 millimeter and fine M6 by 0.75 millimeter socket cap screws. The Unified Thread Standard, UTS, defines a standard thread form in series, along with allowances, tolerances, and designations. For screw threads commonly used in the United States and Canada, it is the main standard for bolts, nuts, and a wide variety of other threaded fasteners used in these countries. It has the same 60-degree profile as the ISO metric screw thread, but the characteristic dimensions of each UTS thread, outer diameter and pitch, are chosen as an inch fraction rather than a millimeter value. The UTS is currently controlled by ASME and ANSI in the United States. Most shops have standard drill size posters like the image shown at the left. It shows standard sizes in decimal and UTS notation, along with drill sizes for tapping threads. Shops also have standard screw sizing boards and templates like those shown on the left. Even with standardization, there are many different options for screw selection. Here we see a few options for socket head cap screws, including head profile and thread length. Example fastener choices typically include the system of measurement, inch or metric, thread size, thread profile, length, head type, head diameter, material, drive style, finish, strength, hardness, and standards compliance. Catalogs like McMaster-Carr have well-organized classification and filtering systems for fastener option choice. It's helpful to define standard screw terminology. The head of a fastener is the enlarged configuration preformed on one end of the headed fastener to provide a bearing surface. The body is the unthreaded portion of a bolt between the head and the threaded portion. The shank is the portion of a headed fastener that lies between the head and the extreme endpoint, and a shoulder is an enlarged portion of a threaded fastener or the shank of an unthreaded fastener. The length of a headed fastener is the distance from the intersection of the largest diameter of the head with the bearing surface to the extreme point, measured in a line parallel to the axis of the fastener. The grip length is the total distance between the underside of the nut of the bearing face to the bolt head. This includes the washer and gasket thickness. A screw thread is the ridge of uniform section in the form of a helix on the external or internal surface of a cylinder. An external thread is threaded on the outside of the cylindrical piece of stock, and an internal thread is threaded on the inside of a cylindrical hole. Pitch is the distance from a point on the screw thread to a corresponding point on the adjacent thread, measured parallel to its axis in the same axial plane and on the same side of the axis. The term pitch is mainly used in the metric system and is specified in millimeters. Threads per inch, or TPI, is a decimal count of the number of threads in 1 inch of a screw thread. The term threads per inch is used for inch fasteners. The major diameter is the diameter of an imaginary cylinder parallel with the crest of the thread. In other words, it's the distance from the crest to crest for an external thread, or root to root for an internal thread. The minor diameter is the diameter of an imaginary cylinder which just touches the roots of an external thread, or the crest of an internal thread, also known as the root diameter. The pitch diameter is the effective diameter of the thread which passes through the thread in such a position that the width of the thread ridges and the thread grooves are equal and lie approximately halfway between the major and minor diameters. This is the effective diameter. A right-hand thread, when viewed axially, winds in a clockwise and receding direction. All threads are right-handed unless otherwise designated. A left-handed thread. A thread is a left-handed thread if when viewed axially it winds in a counterclockwise and receding direction. All left-handed threads are designated LH. Threaded inserts can be used to repair stripped threads and joint components or to strengthen the fastener interface in softer materials, such as a steel screw threaded into an aluminum or magnesium block. These threaded inserts, often known as helicoils, have coils that expand once installed to securely anchor the insert. All of the helicoils have a prong for ease of installation, an installation tool that grips the prong and reduces the coil diameter, enabling the insert to fit in tapped holes. You remove the prong to insert the screw. This installation requires a drill bit, a helicoil tap insert, an installation tool, and a prong break-off tool. Inserts are typically used in non-permanent joint applications where service is expected. The depth of the insert depends on the fastener and part materials. For example, an oil pan typically has a threaded plug in the drain hole prone to over-torquing and stripping. A threaded insert may be used to strengthen or replace threads in the pan. It's important to consider thread engagement for self-tapping screws. A pilot hole should be equal to or smaller than the root diameter of the screw. A rule of thumb is 75% engagement, though that depends on material hardness or softness. Here we see a common workshop bolt identification and mechanical properties chart, including inch steel bolts, stainless steel bolts, and metric steel bolts. You can see the identification mark on the bolt head. Grade is used for externally threaded inch fasteners to designate the strength of the fastener. We see grade 2, 5, and 8 here. Grade 5, for example, has 3 equally spaced slash marks. We also see nominal size and materials for each bolt. Class is used for metric fasteners to designate the fastener strength. The metric class identification marks are shown as numbers on the head. Tensile strength is the maximum tension applied as a loading that a fastener can support prior to or coincidental with its fracture. We see both a nominal and minimum tensile strength in this chart. The yield strength is typically a bit lower. It's the point on the stress-strain curve that indicates the limit of the elastic behavior and the beginning of plastic behavior. Similarly, proof load is defined as the maximum tensile force that can be applied to a bolt that will not result in plastic deformation. In other words, the material must remain in the elastic region when loaded up to its proof load. Proof load is typically 85 to 95% of the yield strength. The hardness is a measure of the resistance to localized plastic deformation, such as an indentation or a scratch induced mechanically either by pressing or abrasion. A higher strength fastener is a fastener having high tensile and shear strength attained through a combination of material types, work hardening, and heat treatment. Understanding fastener finish is important in non-permanent joint design. The term finish is commonly applied to the condition of the surface of the fastener because of chemical or organic treatment subsequent to the manufacture of the fastener. The term finish is also applied to some types of fasteners to indicate the condition of a material surface texture because of mechanical operations and the degree of precision achieved or required. Fastener finish is an important factor in fastener design and selection to ensure full product life cycle. Finish considerations include safety, corrosion protection, resistance to damage and handling, criticality of the joint, functionality, cost, availability, and aesthetics. Common finishes or platings include natural or plain finish, zinc oxide, black oxide, galvanized, anodized aluminum, and bronze, brass, or gold plating. Fastener strength and corrosion resistance are two of the most important factors in non-permanent joint design. Here we see how tensile strength and corrosion resistance map out for various materials. Torque is a measure of turning or twisting force. Torquing fasteners is a critical aspect of non-permanent joint design and installation. Torque tools accurately measure or limit the torque you apply. Using these tools ensures you're applying a consistent torque and prevents over-tightening that can damage fasteners. Selecting the correct torque range is critical. For the most accurate performance, the maximum torque you're applying should fall near the middle of the tool's torque range. So for example, if you're applying 50 foot-pounds of torque, choose a wrench with a range of between 5 and 100 foot-pounds, rather than a range of 5 to 50 foot-pounds. Torque tools are calibrated by the manufacturer. The calibration certificate provides proof of calibration in the date it was completed. Shelf life does not affect the calibration of a torque tool. So common practice is to consider the calibration life to begin at the date of purchase or first use. Standard torque tables, like the ones shown here, are used for most applications. Standards, such as ISO 6789-2003, specify the requirements for and describe the test methods and marking of hand torque tools used for controlled tightening of bolts and connections. It applies in particular to indicating and setting torque wrenches. In evaluating fastening tools, there are 5 general factors that engineers consider most influencing in their selection process. First, ergonomics, measuring the safety and ease of use between the operator and tool during the assembly process. Next, durability, measuring the overall performance, uptime, and maintenance costs of a tool. Then productivity, measuring the tool's speed relative to the time constraints. Accessibility, measuring the tool's ability to access the fastener with operator ease and within takt time constraints. And accuracy, measuring the tool's capability to meet your defined engineering specification. Other tool selection factors may include weight, the weight to torque ratio, operating speed, whether high or low RPM, ensuring low vibration, power, whether that be pneumatic, electrical, cordless, or manual hand power, and a good power to weight ratio, well balanced for low operator fatigue, with a minimal reaction, having a specified torque range, or working within certain industrial environments. Safety wire, or lock wire, is a type of positive locking technique that prevents fasteners from falling out due to vibration or other dynamic forces. A fastener typically has a drilled through hole that the wire is passed through, twisted, and anchored to a secondary fastener or part. Bolt heads in the rotating shaft flange pictured are lock wired in pairs. The presence of safety wiring may also indicate that the fasteners have been properly torqued, a witness wire. Special lock wire pliers, shown here at the bottom, are used to twist wire. Safety wire comes in a variety of gauges and materials depending on the application. 0.8 millimeters or 0.32 inches stainless steel wire is most common in aircraft and racing applications. Thread locking fluids, thread locker brand name Loctite, is an adhesive applied to fastener threads before assembly to prevent loosening. Thread locking fluids come in a variety of strengths, typically designated by color from low strength, removable, to high strength, permanent. Thread locker fluids are specified by the torque to break free, torque to continue turning, and temperature range. Thread sealing adhesives cure anaerobically without air and have thixotropic shear thinning properties. Automation and semi-automation tools and processes are used in most modern manufacturing assembly applications. Technologies include robotic arms, robotic screwing, collaborative robots, pick-and-place arms, pneumatic controls, robot end-of-arm tools, grippers, collision avoidance, and advanced metrology. The Visomatic VCM-3X.2 cobot screwdriver shown here is a fastener feed and drive end effector package that adds semi-automation capability to the collaborative workspace project. This system includes an automatic feeder, programmable screwdriver system, skeleton robot, and end effector for direct mounting to the robot wrist with pre-programmed fault recovery. Here's a summary of the key topics we've covered in non-permanent joints. We've listed different types of non-permanent joints. We've shown how you can select a variety of fasteners for typical joint applications and also identify the attributes of common fasteners. We've shown how you can select appropriate tools and assembly techniques for joint applications and how you can understand design considerations for joint and fastener selection. To learn more about non-permanent joint design and manufacturing assembly methods, check out some of these resources. The McMaster car catalog, the yellow one here, available at mcmaster.com, was referenced throughout. Similar to that is the Grainger catalog and the MSC catalog. Trade magazines like Assembly, available at assemblymag.com, are often helpful, and several handbooks like Mark's Standard Handbook for Mechanical Engineers and Shigley's Mechanical Engineering Design Textbook are also very helpful. Adam Savage from Mythbusters calls the McMaster car catalog his favorite tool in his shop. It's worth checking out his video linked here.